Okay, good afternoon, everyone. Thanks for joining us today. My name's Eddie Galley, and I'm here with my colleagues Abhijit and Ashwin, and we're going to talk about how we scaled up our troubleshooting process for optical interconnects using the Bayer illusion methodology, or BIM, as we like to refer to it internally. So here's what, I think you skipped it. So here's what we're going to cover. Apologies. So I'm going to start off by just giving a little bit of background on some of the challenges when it comes to troubleshooting optics in our data centers. Then I'm going to hand it over to Abhijit, and he's going to give an overview of the BIM concept. He'll talk a little bit about the architecture and then some of the advantages it brings to us at scale. And then we'll hand it over to Ashwin. Ashwin's going to talk about the tool development, and he's also going to take us through some of the troubleshooting steps. And then we'll finish up with a recap, and we'll actually talk about some of the future development opportunities. So on this slide, we see a diagram. This actually shows the Facebook DC network fabric. It shows connectivity from our top of rack switches to the fabric itself and to the spine. All in all, we have approximately 1,100,000 gig optics deployed globally across all our data centers. And so that's obviously why we need a process that, that manages that sort of scale. When we looked at some of the existing troubleshooting tools that were in the market, they tended to be extremely high cost, and they were capable of typically testing one transceiver at a time. And so all of that means it brings high operational overhead. It doesn't really suit our environment. In addition to all of that, one of the things we were finding is that when we were sending failing parts back to our vendors, we were seeing a really high no trouble found rate, NTF rate. In fact, in some instances, it was up to 50%. So that was not a good situation. So really the goal here is, the goal of this whole sort of effort was to find a solution that was efficient and accurate in terms of failing parts, so that we could send them back to our vendors for failure analysis.
All right, thank you, Eddie. My name is Abhijit Chakravarti, and I work in the manufacturing quality engineering team at Facebook. So, as Eddie mentioned, we have deployed approximately 1 million optics globally on the 100G CWDM4 domain. So, when you have this kind of volume, getting the failure parts and giving them to supplier for RMA, it's very challenging, and the number is so huge. Like, it's very frustrating when we go to the suppliers and they ask why it failed for. And in data center, normally what we say, link failed. But what do you mean by link failed? So the suppliers, they need more information so that they can proactively find out the root causes. So basically what we did is, the existing tools are like Eddie mentioned, it's one optics at a time. So the operational cost and the time from the engineers are too huge, right? So to optimize this whole process, what we did is, we took wedge 100 OCP switches and we connected them together. So basically these switches they can run BER. So you don't need any external BER tester, which is very expensive. So these 4 switches we can connect internally, and we can take 128 optics, because 32 ports per switch. We can do 128 optics troubleshoot within 5 to 10 minutes. Because the one thing we can do is, we can pull the DOM information where you have TX power, RX power, TX bias, all this information, as well as the supplier information with the serial number and the revision codes. So all the information we can collect within 5 to 10 minutes using this BIM methodology. And definitely when we send the RMA, the NTF number is almost 50%. So we need to reduce that NTF number, because we are growing every day and we need more and more optics. So finding out the correct good optics is very important for our data center. So with this technology, what we think like we can drop down the NTF rate in a single digit. That's the goal of this methodology. So let me give you some overview of how we are doing the troubleshooting process at our data center. So if you see on the left-hand side, there is one block, blue color. It's saying IQSAP tester, which we will talk soon after this presentation. And the beam, it is like, it's 4 switches together. We are doing all 128 ports, and we are troubleshooting. One part is going, all the failure information is going to the database so that we can track them properly moving forward. And when we ship to all these units to the supplier, we can give them enough information like why it failed. Is it for channel 1? Is it for channel 2? Or is it some bias issue? Or is it some software or firmware issue? So all this information we will get from this methodology. So here are a few advantages. What we see right now is it's a low-cost troubleshoot because you don't need any external equipment to troubleshoot this tool. And also it will reduce the troubleshoot time significantly, speed up the RMA process, and improve the failure inventory tracking system inside our data center. And also the faster response to the supplier, so we can also work with the supplier to find out the root cause proactively and quickly if we know the failure. With that said, I will pass it to Ashwin, who will go over the steps and the software process.
Thank you, Abhijit, for explaining the complex concepts and the end-to-end process for the BER illusion methodology, or BIM. Simplicity is the ultimate sophistication. So the challenge was to distill this complexity and abstract it and come up with a simple set of steps which can be implemented and be made viable in the data center environment. So here are the 3 steps. Step 1, plug in the optics. Step 2, run the tools. And step 3, get the results. So these are some of the implementation details. We built a lab in the data center, which is decoupled from the production environment. We worked closely with EdgeCore to come up with a custom Linux kernel and diagnostic scripts. Based on feedback from the data center operators, we came up with the CLI tool and packaged it using Red Hat Package Manager. We then used the GlusterFS and Chef, which is Facebook's preferred system configuration utility at scale. So zooming in on what the CLI tool does, it first connects to the OCP wedge network switch. Then using the open source CP2112 util, we initialize the optics. Then we set some pre-emphasis values to compensate for the high frequency losses on the PCB bus. We then run the PRBS tests, and then based on the results of the PRBS tests and the DOM readings, we pass the output and come up with the results, which says whether the optic is good and bad, or bad, and also some other associated information. So here is a simple mock-up of how the tool looks like. The only mandatory parameter is the IP address for reachability. And you can have username, password for security and authentication. You can also have time, which is to configure how long the test should run, and log directories. Here is an illustration of how the results look like. So we have detailed vendor information. We have parametric data like TX power, RX power, etc. per channel. We have the BER result output. And finally, we say all the good optics are green, which is pass, and the bad optics are red, which is fail. We also have some auxiliary information like the test station IP address and the test start time and the duration of the tests, so that we can use this for logging and recording purposes. This information can be attached with the RMA, or it can be used for a number of purposes. With that, I'll hand over to Eddie Kelly.
Thanks, thanks, Ashwin. So just to wrap things up quickly, so BIM is highly scalable. We can test 128 parts within 10 minutes and determine what's good and bad. We can also add additional capacity. It's really simple to add additional switches if we want to increase from 128 parts. The troubleshooting time is greatly reduced. and we have orders of magnitude less no trouble found parts going back to our suppliers, which is all good. The parts that we do send back, we send very detailed failure information, which really allows our vendors to quickly FA, root cause, and diagnose exactly what's gone wrong with the part. And then finally, in terms of future looking, we really see this platform, this solution, as being something where we can look at long-term reliability and performance testing. So for instance, laser reliability, I think this would be a great platform for us to start to focus and use to look at that aspect. If you want more information or access to the tools, you can contact Facebook, or it's available via the OCP community. And that's it. So thank you very much. And is there any questions?
Thank you for sharing your work. This 128 port tester, is this one switch that you're using to test all your optics? You plug it all into one switch?
So for this particular methodology, what we did, we used the top of the rack switches, which has 32 ports per switch. But if you want, you can go with the 128 port switches as well.
Okay, so then do you plan to take this into live production, like collect diagnostics similar to this so that you can alert potential poor links that something's about to
So
go bad?
that's a very good question, actually. Right now, what we are doing, it's not running in the live production environment. So we are taking the parts from the failed parts from the production environment and loading it in a different setup, and then we are running this technology. But yes, moving forward, that would be a good addition if we can do it in live production floor.
Okay, thank you.
You're welcome.
How are you detecting any firmware failures? You earlier commented that this tool is capable of pointing out any firmware failures, and you didn't quite talk about it.
So basically, when you load the parts into the switch platform, the first thing we do is the link up test. So if there is any issues in the firmware, you won't get the link up, and you cannot run those BER testing to script or anything. So the firmware test level check would be at the beginning, and then you start the BER testing and all the DOM information collection. Yes.
So I'm trying to understand how big an issue this is. So like over a 1 year period, do you see 0.1% failure, or what scale are we on?
That's a good question. I think we cannot, on top of my head, I don't know the number, but if you really want to understand like what's the percentage of failure for that we are doing this thing,
I think we have 1 million parts, so regardless of what the failure rate is, it's still a lot of parts. So this is the only way that we can really deal with that at our sort of scale, yeah.
I think he's more interested in the exact number. All right.
Okay.
Thank you.